Welcome to the CPACE Podcast, produced by the University of Pittsburgh's Computational Pathology and AI Center of Excellence. I'm your host, Jordan Gass-Pooré, a science reporter covering the integration of artificial intelligence into pathology and laboratory medicine. In this series, we'll explore how AI advancements and pioneering research in digital pathology are not only shaping the future of healthcare and diagnostic excellence, but also fostering new opportunities for collaboration, linking researchers, clinicians, and healthcare companies. From the University of Pittsburgh, thank you for joining us and for following the series. Welcome back to the CPACE Podcast. Today, we're going to speak with James Lindsay, Associate Director and Chief Software Architect within the Knowledge Systems Group at the Dana-Farber Cancer Institute. We're going to learn about the Dana-Farber Cancer Institute's work, their Knowledge Systems Group, and we're going to dig into the role knowledge systems play in enabling computational medicine and research today. To get us started, James, would you like to introduce yourself?
All right. My name is James Lindsay. I've been working at Dana-Farber for almost 9 years now. I have a PhD in computer science from the University of Connecticut, and I was at a startup that failed quickly where I gained a lot of software engineering skills. And for the past 9 years, I've been working on a variety of projects at Dana-Farber, but the Knowledge Systems Group focuses in on two key areas. We build software to support precision cancer research, so integrating genomics and other molecular data and making that available for physicians and translational researchers through easy-to-use interfaces. And then we also support cancer precision medicine. So we build clinical decision support tools like MatchMiner, which helps physicians find patients for their clinical trials.
As a science reporter, could I ask you, what's the Dana-Farber Cancer Institute? And can you tell us a little about your career journey that led you to Dana-Farber and what attracted you to their team?
Sure. So Dana-Farber is one of the largest cancer NCI-designated cancer hospitals in the nation. It's based in Boston. It's been around for over 70 years now, I believe. And Dana-Farber is unique in that it really focuses and splits its resources 50% on patient care and 50% on research. And so this research is kind of like this core value that drives Dana-Farber forward. And that's much bigger percentage than other institutes around the country. I found myself here, I guess, after I had finished my PhD and I was at this startup and things weren't looking great. And I was kind of looking around for a job. And I really liked open source, this idea that you write software and other people could use it. During my PhD, I used basically exclusively open source software tools in bioinformatics and genomics research. And I was interested in continuing that. And I happened to see this job ad for a brand new group at Dana-Farber called the Knowledge Systems. And I had to Google what a knowledge system was. And I feel like the definition changes all the time, but it sounded interesting. And I gave it a shot. And it's been a great experience working here at the Farber. I think our group's a little bit unique because not only do we get to write that open source software, but we do write software that actually makes it to really close to patients to help influence patient care. And that kind of, both of those experiences are like really rewarding. That's why I've been here for so long.
So we noticed that your Knowledge Systems Group brings together an interdisciplinary team of individuals. Can you tell us, why is this so important right now?
Yeah, I'd say it's fundamental to our success. We often find that writing the code is, I don't want to say it's the easiest, but it's only at least a small portion of the battle. And often figuring out what code to write is much harder. So we not only hire software engineers, but we hire cancer biologists and experts in cancer biology who know how to speak doctor language so they can go to meetings and understand what our colleagues need and what they're saying, and they can translate that back to the engineers, or they can take questions and requirements from the engineer and translate it back into doctor speak. And so having that blend of not just engineers, but the domain experts, cancer biologists. And we also have a lot of project managers, program managers, so people who keep us organized. That's also very important in a very big institute like Dana-Farber. There's a lot going on. There's a lot to get distracted with, and having that kind of professional focus is really important as well.
What's personally exciting to you about work being carried out at Dana-Farber? Do you have a favorite area of research that you follow and love to support?
So there's a lot going on at Dana-Farber, and it's often hard to keep track of it all. I think what we're involved in the Knowledge Systems Group that I'm really excited about on the research side is helping organize some of the data and the activities that are around these large NCI-driven projects. So one of them is the Human Tumor Atlas Network, or HTAN, which is basically an NCI-funded project where several different cancer centers are doing a deep dive using multiple different molecular and spatial profiling technologies on different cancers and even pre-cancer individuals. And we've been working on this project for the past 5 or 6 years. And there was a recently big release in Nature of, I think, 16 or 18 papers that came out. And it's super cool seeing all of the great science that gets done all over the country. And then it's really hard from our aspect to help organize the data and get scientists to submit metadata spreadsheets with this, the appropriate headers. But all of that activity has been really exciting for us because it's going to let other researchers reuse that data in the future. It's something that gets me really excited. And we're always looking out for the next big project that we can support in that way.
I'm sure that all of you who are working on the technical side of supporting Dana-Farber's work find yourselves intrigued by all the scientific work, and in reverse, maybe all the science and medical folks find your work just as interesting.
Yeah, I think that's really an exciting part about working at Dana-Farber, and especially within our group. We're always in meetings with physicians. Yeah, someone's always saying oh, I wish I could just code this up myself because the doctors know what they need. And sometimes we're like, well, what did that person just tell me? I need to go back and look up all those words because we don't understand the doctor speak. But that cross training would be great. But besides going back to medical school, we try to build this collaborative environment where the programmers and the physicians are all in the room together and work closely.
Speaking of computer science and data science and educational opportunities, are you seeing doctors, for example, getting into coding?
Yeah, I think fundamentally we're starting to meet more and more doctors who have exposure to computer science at a much earlier age in their career, and we're seeing more doctors that program. I think that's, it's kind of like learning a language, right? You're learning a programming language just like you might learn, a normal language to communicate with someone. It's kind of the same paradigm. So I think helping physicians get comfortable and exposed to coding and statistics and data science as part of their fundamental training is happening more and more. And I can imagine in the future, there'll be a lot more of that as well. And then the other side is we try and expose the programmers to biology and genomics. So one of the great things about being in the Boston area is there's the Broad Institute, there's Harvard Medical School right across the street. There's so many lectures and kind of events that you can go to try and gain some of that medical or biological knowledge. And we really encourage for everyone, whether it's a postdoc or staff here, to take advantage of all those resources.
All right, so getting back to knowledge systems, looking ahead, what's challenging and exciting about your work?
I think data has always been a limiting factor in a knowledge system, right? To build knowledge, you have to start with data, and then you curate it and you massage it, manipulate it, bring two data points together, and then at some point it becomes knowledge that's actionable. And in the past couple of years, with the advances that we're seeing in AI, the ability to get more structured data into our databases and to our knowledge systems has really advanced. I think in healthcare, and this isn't a secret, right? The data is kind of really messy, right? The way physicians collect and hospitals collect data is in these medical record systems is often just a 21st century, it's a digital version of the doctor writing it down on paper. It's free text. And that's been a limitation in cancer and medical research in general, is in order to get structured data that you can feed into statistical models to make new discoveries, you had to pay someone to go through medical notes and structure it for you. And now in many different ways, AI is helping us, and large language models is starting to help us understand how we can automatically read this unstructured data and add the layer of structure. And that's opening up lots of different opportunities. I see the knowledge systems group is helping with some of that fundamental activity, like just structuring some of the data and getting it into the databases. But we also want to be on the kind of more patient-centric sides. One area we're really focusing on is clinical trial matching. So by having more structure to the patient's medical records, we know more about the patient and we can better find trials which that patient might be eligible for, make recommendations to physicians around that. But there's plenty of other use cases there. Translating physicians' notes is one active area of research I've seen at the Farber, and there's a lot of interest right now. When you go to the doctor, this is federal law. You're supposed to get access to your physician's notes right away. But reading the doctor speak is hard, like I've been saying. And so, some folks are interested in figuring out a way to translate that language into a way that's more approachable and understandable, and even translating it between different languages for people where English isn't their first language.
I'm curious, thinking about your day-to-day at Dana-Farber, when you're coming into work, what kinds of challenges are on your mind?
Yeah, I think with the projects that we're involved in, we think a lot about what's the right way to use new technology, whether it's a large language model that's structuring text or kind of extracting information from text, or whether it's like a digital pathology model that's making some assessments of a pathology or radiology image. I think trying to understand how that fits into the medical space is really complicated. So there's a whole spectrum of how technology can get used. Right? At one kind of very formal end of the spectrum might be like some FDA approved tool, right? That's gone through prospective clinical trials and it's been validated at multiple hospitals. And, that's great, but it's really hard to get there. And then, at the other end of the spectrum, it's research, right? And, it's never going to make it to a patient. And so it's, you do your best to get good research results. And the knowledge systems group often sits somewhere in the middle, where we're helping with translational clinical trials or studies. And we're trying to introduce new technologies. And it's really complicated to think about. Some of the problems we think about is how do we convince physicians that what we're doing is correct? Like, what are the error models and bounds or statistical bounds we could provide on a new technology? It's trying to convince like institutional review boards, IRBs, that what we're doing is ethical and appropriate. We have to make it very clear that what we're doing has benefits, or there's very little risk in how we're doing it. And so understanding that landscape is complicated, and it's even more complicated with the newer tech.
Speaking of something that's complicated, can you tell us about the architecture behind your knowledge system? Do you have like a giant centralized computer living in the basement? And how do you handle all your data?
Yeah, I think on a technical side, I wish there was a master database. You see sometimes fancy spreadsheets, or not spreadsheets, slide decks on how you can leverage cloud provider X's, data studio to organize everything in your business. But in reality, it doesn't end up working like that, especially at a large academic medical center, right? There's a real hospital that's running, and there's lots of data sources, whether it's, kind of more business related or patient related, and all of that data has to get integrated, and it's all very messy. So what we tend to end up doing is building the knowledge systems kind of more for a particular product or end goal. So for example, in our clinical trial matching work, we integrate sources probably from a dozen different systems, and we have to categorize and quantify like what the reliability and the variances are you get in all those different data sets or sources. And those kind of calculations really only apply for trial matching. So we end up kind of, I would say, with a bunch of, we have like a data lake that the Institute maintains. It's the source of data, and everything ends up in it. And then we have to like kind of massage it and curate it on an application by application basis. But of course, we're always working towards a more modular and grand vision of things. It just, I think, takes a long time.
On this podcast, we try to incorporate two special questions into our interviews, one from a student and one from industry. For a twist, I'd be curious to hear what sorts of questions you hear from students. What kinds of things do they talk to you about?
Yeah, I think there's been so much kind of popular media around AI recently, whether it's large language models or generative image models. And so like students know all about this kind of fundamental technology, and they even hear about how it can be used in medicine, but they're really interested in the reduction to practice. And so I don't think they understand as a student how complicated it is to kind of take some of this new technology and bring it to the clinic, right? Like, and so we do get a lot of questions. We're at the water cooler or down on the street. It's like, okay, what are you doing? And we say, oh, we're working on trial matching. And so we'll get questions like, oh, that's awesome. You're using AI to put patients on clinical trials. And then it sparks this conversation like, no, not really. We're using AI to help reduce the list of trials that an actual doctor is going to review. before they go onto a trial. And so we kind of always talk around like kind of more like reduction to practice area that I think if you're not embedded in the medical space, you don't really understand all the complexities there.
So speaking of AI, we do have a question from Alex Pomp, a research manager with Meta's Data for Good initiative. Alex is curious to hear your views on the usefulness of emerging machine learning models to teams like yours, and he'd be curious to hear your views on smaller models. So, what are your views on the integration and use of smaller models, which we tend to not hear a lot about in the headlines? For example, Llama's 3.2's 1 in 3 billion parameter model versions. Alex shares that the smaller models tend to not grab the headlines in the performance metric race, but his guess is that they are often deployed more often and for a greater range of applications, which is perhaps quite useful as we're still discovering the most intriguing use cases that LLMs are well suited to cover. As a preface, though, and before you answer, I understand that your team participated in Meta's Llama Impact Grants program and that you guys won an Impact Innovation Award. All right, congratulations on that. And maybe you can also tell us a little about your Match Miner project and how did y'all incorporate Llama into it?
Yeah, so we were fortunate to be selected as a winner of the Llama Impact Grant in the Open Innovation category. And our pitch was that we were going to use Llama, our large language model, to help facilitate recruitment for patients into clinical trials. And we use both large language models like Llama, but under the hood, we're also using smaller models, such as what they're called like Roberta-based models, which are maybe a generation or two behind the large language models, but it is fundamental to how we build a real clinical trial matching system. I guess to start from the beginning, I'll give the kind of the one full sentence overview of our trial matching process. Is we use the large language models to take a patient's medical records that sometimes get updated daily. We leverage its summarization ability. So large language models have been known to be able to take a corpus of text and summarize it concisely. But so we do that nightly, and we can also ask it to summarize the eligibility criteria of clinical trials. We came up with some specific prompting strategies for these large language models to decompose the trials to what we call trial spaces, which represent the main clinical criteria a trial might be targeting. And sometimes trials are targeting multiple different criteria. It could be a trial that's targeting different cancer types, so this would be in different trial spaces, or it could be the same cancer type, but patients might be divided up by what prior treatments they've had or something like that. That's our first use case of the large language models. But actually, in that process, we do use small language models. So while the large language models are great, but your medical record is really long. And there's often a lot of copying and pasting. I don't know if you've ever checked out your own medical record when you go to the doctor, but they'll often just copy and paste like the whole text you got from the last encounter. And so we do train small language models to help us classify portions of the text that are going to be relevant for defining these trial spaces. And so rather than trying to get some massive supercomputer or some bleeding edge large language model that can process all of that medical record in one shot, we were able to prompt it multiple times and extract the relevant text using the small language model. And the other way we use small language models is actually when a physician or at Dana-Farber, or even someone who's not associated with Dana-Farber, but might want to refer a patient to Dana-Farber. We built the software, which isn't live yet. This is all still under development, but they can enter a summary of the patient, and we use in natural language. Like, I have a patient, metastatic breast cancer. They might describe the prior treatment. And we use Llama to summarize that down to the criteria we use. And then we use what's called an embedding model, which takes that short summary of the patient and embeds it into a vector space, which is a series of numbers that we've trained specifically to bring in this vector space the patient closer to clinical trials that are relevant for that patient. And so we're able to build a web app that can quickly, given a summary, it'll almost instantaneously be able to find a few pretty good recommendations for that patient's summary.
I noticed that you mentioned vector databases. What's interesting about them? How are y'all deploying them? And what are y'all learning in the process?
Vector databases have definitely emerged in the past couple of years of being super important, and there's lots of them to choose from. We use the simplest of a vector database at this point, which is actually no database, because the data is small enough that it fits in memory. And that happens, I think, in some places, in the medical space. We're still struggling for data, and that's one of the hardest things. So we're able to encapsulate or take vectors that represent our patients and our clinical trials and have them all in memory on our kind of servers. But as these systems grow, we'll definitely have to explore different databases, so that we can have a corpus of information that doesn't fit in memory but still get fast retrieval. And they're often used in operationalizing these AI workflows. And so you need to make these comparisons really quickly to find some information. And that's where the vector databases kind of stand out. But I would say with my engineer, what did I call myself? Chief software architect, right? With my hat on there, the best database is no database, right? It's always keeping things simple until you really need it. And so it's great to be in a position where you have so much data that you can't keep it all in one machine. And then that's a great time to use vector databases. But before then, just keep it in memory.
That's interesting. When you say that you keep data in memory, how much data are we talking about?
Yeah, for Dana-Farber sees, I think, over 100,000 patients a year. And so our data pipeline for trial matching is, we take the medical records and then we run Llama to summarize it. And so in the end, though, even though we have 100,000 patients, probably with millions and millions and millions of words of text describing them, we end up with a very small paragraph summarizing these key criteria for the patient. And so the database or the total data that could go into this trial matching is probably only a couple of gigabytes at most, because it's been compressed into the most relevant content.
This is a slightly nerdy question, but do you create your own vector encoders?
Yes. So that was a big part of our work, and we're working to get a preprint of our process using Llama and these BERT-based encoders. But we do build our own encoders that we're calling this trial space encoder. And what we've done here is we've taken retrospective or historical enrollment data. So we know when patients have gone on a clinical trial, and we know we can summarize the patient at the point in time when they've gone on the trial, and we have the summary of the trial. We can train an encoder to bring those two summaries or those two concepts close together in this higher dimensional space. And that's kind of the backbone of our trial matching process.
So one of the reasons that we wanted to have you on the podcast is because knowledge systems are super important, but we don't hear much about them, and they probably require a considerable amount of work to maintain. So can you share for us, how do you manage the health of your knowledge system? What does this entail, and what kind of advice can you offer CPACE and other similar initiatives supporting computational pathology?
Yeah, I guess there's two aspects to that. So one is like the code and the core technology, and how do you maintain that? And then the other aspect is the operations of it, right? So whatever that knowledge system is feeding. And I think they have different distinct requirements. On the code side, a great example of this is the cbioportal.org, is this open source knowledge system that we maintain. And it's got a very active user group. We get dozens of questions a day through Google Groups, and we have to be organized. Someone's always on duty each week to make sure that we're responding to those questions. And usually it's easy, like, how do I do X, Y, and Z? And you just kind of, copy and paste your answer. But sometimes we get insightful questions that lead to new developments or bug fixes or something like that. And so having that customer service mindset, I think that when it comes to the core technology is important, whether it's totally public like CPACE or even internal, you gotta support it and have a way for people to complain. And then I guess on the operational side, it takes a lot of work. So for our clinical trial matching, so we've launched MatchMiner, which isn't using AI, it's just using genomics. And this has been in production for over 8 years. And it takes a daily group of engineers and cancer biologists to support this. We're getting data from genomics feeds, and we have dashboards out, in our lobby that shows overnight, did the data come in or where were the bugs? And we have daily stand-ups to discuss, problems with the data feed, confirm everything worked. And there's, a weekly and quarterly review of the data to make sure everything is still up to snuff and nothing has failed. Clinical trials are still properly defined and everything. So it takes this a team of people really invested in supporting the system.
Thinking about the future of work, how do you envision we'll be working in the future?
Yeah, I think we will do more. I mean, my general philosophy is we're going to do more with the same amount of resources that we have. So, we're willing and interested in experimenting with AI, how it can support research or, clinical decision making at some level. But we're kind of treating it like any other technology that we might onboard, and we're getting really serious about evaluating it. We have some colleagues here at the Farber who are doing some pretty deep research and evaluating LLMs for clinical decision making. And they're just, they and others are finding holes in how they work. And so, we definitely have a pretty big level of skepticism going into it. And we've still got a long road ahead of us to prove how this tech is safe and useful in research in the clinical setting. But that's what gets us excited. So we're excited to do that.
You mentioned evaluating LLMs. Out of curiosity, have you formalized a set of questions or a process that you use to evaluate LLMs?
I'm not sure. I mean, there's definitely been some recent research work kind of talking about that more generally. I think from our perspective, we almost treat it, like I said, just as any other tool. So like for the Impact Grant, we're going to run a clinical study, in collaboration with physicians who are going to review everything. And it's not a clinical trial, it's just a study. So it's only exploring like the operational impact of using AI. It's not really changing the patient's outcome. But we're gonna do that study and see what they think. We'll get the clinicians exposed to the data and we'll see how often it works, and they'll tell us when it doesn't work. And we'll publish that. And I think lots of people are going to be following that paradigm. And in I think a short amount of time, we'll get some pretty good maybe takeaways from the community. I'm not sure I can offer any right now, though.
All right, to start to wrap up our interview, I wonder if you'd like to give any advice to students who want to get involved in computational health and medicine. What's your message for young people?
Yeah, I think so. Computer science and AI is involved in everything we do now. And so I think I would definitely encourage folks as soon as you can to start taking those core classes that underpin that. So statistics, just basic statistics is super important. You don't have to be able to write your own large language model to use it, but if you're going to evaluate one, you're going to need to know, the basic statistical concepts, and being familiar with that is, I think, super critical. I'd really encourage folks to keep reading. There's publications coming out all the time, and the use of archive and these preprint servers makes them accessible to everyone. And so you just keep an eye on, your Twitter, your news feed for these cool publications, and just take the 10 minutes to skim over these papers as they come out. And then at least you'll be familiar with some of this technology. And when you get the opportunity maybe to work on something similar, you can jump on it because you have a little bit of knowledge about it.
How about messages for companies? Like one's interested in experimenting internally with large language models like Llama. What's your advice?
Yeah, I guess that's one thing I didn't touch on, which might be applicable is, because we can bring the code inside Dana-Farber and we have the resources to deploy it locally. It really changed the game when it comes to designing studies to use it. Right? So if you're using a public API, even if you have contractual relationships and what we call these business associates agreements, there's still an element of risk with sending, patient data out to other people. And we don't want to harm Dana-Farber's reputation or, harm the patient. And so people are very, wary, I would say, of some of the public AI, and rightfully so. But because Llama is portable, and it's open and we can bring it inside our firewall, really kind of simplified the game. We're probably going to have a lot less meetings with lawyers than if we had used some sort of, cloud-based AI system.
That's interesting. Out of curiosity, would you walk us through deploying Llama internally? And what's your advice on testing a small model, for example?
Yeah, so I guess my advice for getting started with using these Llama or LLMs or the small versions is just to do it. So actually our first use case, first time we used Llama was the small Llama, I think 3 billion at the time, and I just ran it on my laptop, and it took 15 seconds to summarize the synthetic patient note. But but it actually did it. And it got me really excited. And so I would say just do it to get your feet wet. And then you can show demos of what you've done to folks to get the support that you might need if you want to scale things up for your laptop. There's nothing stopping you. There's great open source libraries. OLLAMA is one library. You just download it, it's point and click, and you can have the power of these language models on your laptop.
James, it's been an absolute pleasure speaking with you. Thank you so much for joining us on the CPACE podcast. From the University of Pittsburgh, thanks everyone for tuning in and for following the series. Join us again soon to hear how AI is not only shaping the future of healthcare and diagnostic excellence, but also fostering new opportunities for collaboration linking researchers, clinicians, and healthcare companies.